thank you for coming. We're going to do a brief little talk about neural networks and then, just like hang out and stuff. I don't know. So, alrighty. So, I'm going to talk a little bit about neural networks, talk a little bit about ethics, and then, just some closing remarks. So,
all right. So before we get into like neural networks, we're going to talk about for like 2 minutes about this really cool data set. It's called MNIST, guys. And MNIST is basically a bunch of black and white numbers. And the entire point of this is we're going to try and build a neural network that will classify these numbers. So given an image of like this 3, our neural network should be able to predict that it is a 3. And that is the entirety of the MNIST data set. It is just a bunch of numbers in this format. Anybody else have any other remarks about MNIST and its glory?
One of the reasons why MNIST is considered so important is because the start of what we call the convolutional neural network, which is something you'll learn about in advanced track, is basically from MNIST, or like a very adjacent data set. So this was like back in like the 90s. There's really famous machine learning scientists, or famous now, but I think it's called Yang Ku, who was basically working with USPS to do one very specific task, something called optical character recognition, which is if you have a candidate written like some word, some English word, how can we turn that into the visual version of all that? And it's seeing how that being very helpful for USPS because you have all these like handwritten addresses, 3 letters and packages. How can we make sure it just gets turned digitally automatically so it gets better processing system? And basically, it was with the help of a neural network that they actually managed to make the system work. And that's how we went from literally rooms and rooms of people sitting in front of a computer, seeing scans of handwritten mailing labels and typing it into the computer system to now only needing one existing among these facilities left in all of the US for really, really difficult edge case mail labels that machines cannot, just do optical character recognition. But Tom Sauce will do a great video on it. But this is why, and this is so legendary. It's basically a subset. All of that optical character recognition data sets that sort of specifically has to do with just the numbers, and it's kind of like a hello world of a lot of neural network and machine learning projects.
Because not all of you are going to take economics. That's something called creative destruction. Yeah, back to it.
Yeah. Also, if you ever like do research and they ask you to benchmark something for like a convolutional neural network, and then they decide to like split up your CNN into different things, you will most likely be asked to run it on the MNIST dataset and predict its accuracy using that. So I have personally used the MNIST dataset simply just as a benchmark because of how famous it is. And there's some great models out there that work really great for this stuff. Okay, so now onto the actual neural network portion. And basically, all of our examples are going to be focused on this specific data set and kind of seeing how a neural network may try and recognize a number like this. So when we think of neural networks, hopefully our mind also goes to something a little bit closer to us as humans. The inspiration for neural networks is mostly from how human brains work. Human brains work when we fire neurons, which will lead to other neurons firing. They get activated, and that causes us to do something. And so neural networks decide to take a very similar approach to that. And so the first thing we're going to define is what does it mean for a neuron to fire? And so in our case, a neuron is anything that holds a number between 0 and 1. And so in the case of grayscale images, 0 and 1 can be the grayscale value that we are holding. So 0 is black and 1 is white. And so this number is called the activation number. And in this case, if we have a number that is 1, our neuron will be firing. And if we are at a lower number, we will not be firing that neuron. And you can think of like a value in between being like, okay, we're like firing, but not with as great intensity. And we'll see how we can like use that to deduce our output later on. So that is kind of the association between a neuron and a neural network and kind of that notion of like what happens in our brains. All right. So this is a beautiful image of a neural network, and it has a lot of lines. Okay. And basically, we're going to go back to the human analogy here. So in the example, when your brain wants to tell you to raise your hand or just raise your finger, what happens? There's a signal that goes from your brain down your neck, down your arm, down your forearm, and then to your fingers. So let's divide this up into like a bunch of different parts. So first, your brain will fire, and it'll tell something needs to happen on the right side of my body. Okay, then it's gonna go say, okay, we need to activate specifically the shoulder, then the forearm, and then our finger. And so let's think of these as different layers in our neural network now. So as we're going through these different layers, we are going to try and activate different things. And so the best way to kind of look at this is if you think of these numbers in this data set that range from 0 to 9. Okay, we have, let's see, it's a good example. Let's take 9, 8, and 1. If we want to identify these, we can kind of look at distinct parts. We can say that 8 can get divided into these two sort of circles. The 9 can be this one circle with a single line, and this one can be composed of these 3 distinct lines. And so now what we can kind of think of is each of these neurons is trying to identify each of these subparts of these numbers. And if we recall the activation, we can say, if we are recognizing this part and this part, we are going to give it a certain weight so that it recognizes it as an 8. So the entire idea in this slide is, you see this last layer right before the yellow box? Ideally, that last layer would be identifying each of these like subparts. And then when we connect it, we say, oh, we've identified these two circles. Our final output is an 8. We've identified a circle and exactly one line, so our output is a 9. And that is kind of the general idea of how we want a neural network to work. How we train this and how we decide those weights, things like that, we'll cover in advanced track. But the idea here is just to give you a general intuition on ideally how our neural networks would work. But it's very hard to like sometimes get this exactly for other data sets and things like that. But this is the intention of a neural network. You're basically, in many ways, trying to divide it up into like a subproblem and say, okay, I'm going to identify these parts and in these parts and then combine them in some sort of fashion. And so that is why you see all of these connected lines. It's basically saying your inputs of a previous layer will affect the output of the next layer. Okay. All right. Any questions about like the general notion of how we want a neural network to work, or like the relation to like the human side of things? I'm not a biologist, but like, yeah.
Like why like this vision part is more difficult compared to the other part of the knowledge. It's like us humans, we actually have like this millions years of heuristic built in us, like as a species, like we have experience, we see something, like we have like certain conditions. Like is it why like, it's kind of like difficult to recreate this with AI?
Yeah, so we try and loosely base neural networks off of like human biology, but unfortunately, we don't even know how the human brain works completely. So like to your point of like, how do we identify things? Neurologists and people like that, they don't exactly know everything that happens inside of our brain that allows us to identify things like that, because our brains are so much more complex. They have way more neurons, and the connections that form are very different. So the human biology like portion, like the relation we're trying to make, is just as like a general idea. It's very loosely based off of the idea of like we're firing something that causes something else to do something. I wouldn't try and think of it in terms of a human brain, because neural networks are just not there yet, and I don't know if they will be, because the human brain is just that complex, and we also don't understand the human brain that well.
Identifying like matching people's different styles and reading to like text. Is it related to neural networks?
Yeah, like most optical, again, that's called optical character recognition, right? Like most optical character recognition things today are able to decently well be able to, you know, like translate people's handwriting into actual characters. Because if you think about it, optical character recognition is not just, oh, what is this character? Is you're given an image with a bunch of text in it, and not only are you trying to first localize where each of the characters are, but also then like string them together and be like, oh, that's a coherent word. You know, where's the space? You know, it's a more complex version of just classifying, you know, like whether it's a 0 to 9 digits, right? But nowadays, yeah, it is very, very accurate. Like in fact, like that is why even though there's still like quite a lot of handwritten mail labels, most of them, like at least with USPS and most observants are able to just kind of parse that almost automatically and be very confident that this is going to be accurate, and and not have to have someone actually do it to check it out. And like even just for the in this data set, for example, it is like especially with PyTorch, since like PyTorch a lot of layers and stuff here implemented for you, it is relatively trivial to get like 99% accuracy on an average data set. Like if you want like a decent challenge, quote unquote, and this is a great way for you to check, is my model going wrong? Like it's a nice sort of like sanity check situation. But then what people use nowadays mostly for like the first step of can I get to like just getting 70 to 80% accuracy is good is something called Cyclar 10, which is a very similar 10 10 class classification problem, but instead of black and white, it's actually color, so it has RGB channels at 32 by 32 resolution, and it has just 10 classes, all classes like birds, cars, truck. I think a frog is in there, there's horse, car, something like that, and just 10 of those classes. So yeah, there's like a few sort of very common image classification data sets, and if this is the hello world, then like what I was saying about Cyclar 10 is kind of like the let's write your first complete program sort of thing.
This is all covered in advanced track. Also, one other important piece of like context to know whenever you're talking about accuracy of models is models like can never be perfectly accurate, but then again, like humans also can be valuable, like if I showed you like every single like 10,000 randomly written numbers, you might not be able to identify all of them. Like what if I wrote like this like weird like little number here, like is that a 4 or a 9? Like you can't really tell me. And so to expect perfection when we can't really ask that of humans is a hard thing to accomplish.
And in fact, again, we cover this in the advanced track where we can go over the entire history of image classification. Is the current, or I guess, image classifications is kind of basically considered a quote unquote solved problem in that we have since 2015 been able to surpass human performance. So just a little like very quick preview of what we do talk about in advanced track is there is this data set out there called ImageNet. It first came out in around 2009, 2010, something like that. And basically it is 1 million images and 1,000 classes of images. So it's like a lot more detailed class labels like pandas, grapes, raspberries, like really like more detailed classes, 1,000 classes, around 1 million images. And they run this competition every year. Basically, all they ask is we have these 1 million images, you can use that as training data. We have these testing images that we don't release. And basically, who can do the best? Who can have the best accuracy, right? And usually the metric they go for is top 5 accuracy, which is the model predicts the top 5 most likely, classes. And if any of them are the ground truth or correct class, then that counts as a correct, successful attempt. So basically, a bunch of Stanford researchers got bored at some point and went, oh, I wonder what human performance is like. So they sat down one weekend and just started manually classifying a bunch of images, and they found that human performance for top 5 accuracy is around 5%. 5% is like 5% error, right? So like 95% accuracy, which is pretty good. But then we actually managed to surpass that in 2015 with the ResNet paper, which introduces something called residual connection that we'll talk way more about in advanced track. But that is a fundamental paper that I believe it is the most cited paper, like period. It is the most cited paper because first of all, machine learning is a really, really big field, and it's really easy to generate a lot of citations in machine learning, like compared to other fields. It's obviously so difficult to get citations, but it is the most cited paper ever, I think, at least in computer science. So just putting that out there. So like that's why like these are really useful tasks how we understand them. So a lot of places research nowadays isn't really on image classification. We have kind of moved off of classification generally because that we have found we have managed to almost completely solve the classification problem, because what we found is we just make the models go deeper, make the data set go bigger, and then things just kind of work out. So like a bigger question nowadays is actually what we call open words classification, which is like you're given an image, and without telling it, the model's just able to tell you what that image is, and without any sort of 1,000 predefined classes. You can think of like ChatGPT Plus, or GPT-4 is able to do this, where you can give it an image and tell it, hey, describe this image for me. Then it's able to use natural language to describe what the image actually is. And these like multimodal large language model and this visual model combines things are able to kind of reason about images and string together in natural language. And because these models exist, at some point we kind of go, well, what's the point of developing cutting-edge image classification models? Obviously, there's still a place for smaller image classification models for places where computation power is limited, or the task itself is very simple and you don't solve the complicated things. But like this task of image classification itself has kind of reached a point where the human scientists are not as interested.
It's like, the bird part's like impossible as it was like in 2013. But nowadays you just see it and it's just like this ages really poorly.
Yeah. Yeah, so image text. Yeah. Yeah, in fact, that's a whole thing where like just a single clip, it's a contrastive learning. So what I think we're trying to do is try to create embeddings of text and images that we have text, a bunch of text images shared with them so that the embeddings both contain text information and image information. That's kind of the basis of a lot of text image models. In fact, this Saturday, I'm giving a reading group, but I'm going to be giving a reading group on all things diffusion models. We build everything from scratch about computer vision, and we're going to talk about what machine learning scientists have been doing with diffusion models nowadays, and AI and all that stuff. Anyway.
All right, so back to basics.
I do want to say one last thing about everything about neural networks. Image classification, specifically when we talk about neural networks, from a mathematical standpoint, we know absolutely nothing about neural networks. It is an ongoing area of research. So everything that we studied so far in beginner track, there are mathematical proofs that I can write out for you guys on saying it will achieve this accuracy within this amount of time.
You should, right?
No, I do not want to. Unfortunately, with neural networks, we don't have anything like that. The math behind how all of this works is there, but we are not able to kind of make it, I don't want to say concise, but make it general enough to say that we can learn certain things like we can with other models for certain types. There are research papers right now that exist saying, given a 2-layer neural network with these type of connections, that we can guarantee this level of performance, but those are very specific. And so that is one area of research where neural networks, the practice and implementation and being able to use these on different models far surpasses our theoretical understanding of why these things work. And so part of the reason we want to give like such a broad overview is we don't know how all the theory necessarily works. And we don't have the guarantees.
It just works.
Yes. Neural networks just work.
Yeah. So if you're like really in this situation,
We'll have time for more discussion at the end. But we do not want to take up too much of your time. So we'll really quickly continue. Sorry, Jordan, continue on.
Oh, I guess it's my go. So the primary unit within neural networks is something called an artificial neuron. Like Venkat said, it's modeled off of biological neurons. However, it doesn't really represent anywhere near the complexity that these actual neurons can have. Biological neurons can have multiple different types, can have much more complicated nonlinearities compared to an artificial neuron. But for our case, this is sufficient. Essentially, it represents a fake neuron. Now, remember, logistics regression was essentially given a weight vector W and an activation function sigmoid, we return Y equals sigmoid of W times X plus B. In short, what neural networks do is just extend that out to multiple different layers and using multiple different activation functions. So in a single layer neural network, we have something called the input, the hidden, and the output layers. The input layer is just whatever you want to feed in, whether that's an array of pixel data that you've turned in, that you've created from an image, or an array that represents a string or a piece of text. The hidden layer is essentially what actually acts upon the input and then passes that forward into the output. The hidden layer essentially takes the input from either the input layer or the previous hidden layer and applies its weights and its bias and another activation function. So if you wrote out mathematically a multi-layer neural network, you'd essentially get an activation of a weights times an activation of a weights times an activation all the way down until you have your full neural network. So why do we really bother with neural networks? You know, we've kind of covered all these other methods that seem to be sufficient, right? In short, neural networks are able to do things that logistic regression, linear regression, and any other form of classical machine learning, as they're known, can do. It can represent nonlinearity much better than anything that we've seen before, and it really just allows us to model more complex data. Training for neural networks gives us a greater ability to model any form of data that we're given, so long as we treat it well enough to be useful input for a neural network. Now, there are more complex architectures within neural networks, such as convolutional neural networks, recurrent neural networks, but those focus on specific applications and help us with nonlinearity in those cases that really other classifiers cannot represent. We also have a really cool demo to illustrate all of the ideas that we've covered. You can access it on the slides, which I believe are in the resource.
The asset cluster.
Cluster.
But now we'll talk to you guys a little bit more about it. It's a really interesting demo. I'd highly recommend checking it out. But now we're going to talk a little bit about ethics, namely explainability of AI, which we kind of already touched on a little bit, if you guys remember, when we were sort of like, AI is like a black box, you know, like that's a very common term you hear. And, you know, as we discussed, you know, we don't really have like a full understanding of, you know, exactly like everything an AI model is doing. Well, it's very simple models, we might be able to achieve that. But for most like modern applications, like ChatGPT and stuff like that, you know, it's sort of like, I don't know, like a magic monkey that you can poke with a stick and like it does something and it works pretty good, but you don't know what's going on inside the monkey's brain, you know? But, you know, this does raise a lot of ethical considerations. So one here is like, you know, a doctor comes back to you with a diagnosis from an AI model. How much would you trust this diagnosis? Would you trust this more than the doctor? And what if the doctor couldn't even tell you why the model arrived at that certain diagnosis? So like, for example, I don't know, say, you know, the model tells you, you have like a really complicated AI model and like, say it's like 98% accurate, you know? And it's, I don't know, it's predicting if like you have tuberculosis or something. I'm not a biologist, right? But it's doing something like that with like 98% accuracy. And say the doctor has less accuracy. I don't know, like 95% accuracy, you know, still pretty good. But the AI model is like much, you know, is significantly better. You know, like if your doctor is 90% accurate and the AI model is 98% accurate, the AI model is going to be wrong 1 out of 50 times. But with the doctor, it's going to be wrong 1 out of 10 times, you know? But, you know, one of the key differences between it is if you ask your doctor to like, be like, okay, why do you think like I have tuberculosis? The doctor's not going to be like, oh, just vibes, you know, like, but that's basically what the AI model is doing. It's just sort of being like, that's tuberculosis. I'm telling you, like, trust me, you know? And so this raises, you know, a lot of, you know, ethical concerns. Like if you were making a decision about whether or not to go into like a dangerous surgery and you were having to base it off of an AI that wasn't, you know, able to like explain its logic and stuff like that, how much trust would you put into it? You know? And so this is, as we discussed, especially prescient with neural networks, like the ones we discussed today, and how, as we mentioned earlier, like we just sort of observe that it works, but we're not always 100% sure why and how it works. And this is a really interesting growing field. Honestly, not super close to like being able to like explain to you how ChatGPT works and stuff like that. You know, it's really interesting. You'll see stuff where it's like, you know, we thought that, you know, this approach to making a model worked because of this, but then we changed it and it worked pretty much the same. So now we're not exactly sure what's going on. But, you know, in general, there's just a lot of linear algebra and pour a bunch of data in and we shake it around and then it sort of does something for us. But, you know, it's just something to be very aware of, you know, when you're talking about and analyzing AI. Obviously, this is a very short introduction. I would encourage you guys to look into it more. There's a lot of fantastic resources really talking about it. But it is something to be aware of. So any questions about like ethics? Yes.
Yeah, so basically like the process of how it's done, like how we map the input to the output is still largely unknown.
Well, so we know the sort of math we're not always entirely sure what exactly like the relations it's pulling out are, right? Because you start off with like a neural network, and it doesn't really know anything. But the big picture idea is that you can train it to take in an input and based off those inputs, do a bunch of like, linear algebra and output something that you desire. You show it like I don't know, you show it like a 3, right? And you tell it that it's a 3. And then like it learns that was a 3 and it makes a prediction. And then you tell it, oh, you predicted it was a 3, that's right. Or it's like, you predicted this was an 8, that's wrong, And then over time, we know how to make it so that it's going to like improve, and be able to iterate and, take this sort of feedback. And again, this gets into like the, a lot of stuff we talk about like in advanced track, but if you remember like gradient descent, like the idea of you're trying to minimize the loss, basically you're trying to do better and better at this. And so it can get better and better at this, but a lot of times we don't always know like what's, exactly it's doing to like pull things out, like for example, I think that there was like a fish recognition thing where it pulled a bunch of like images from the internet. And they did this thing where they could see what parts of like the image the model was really paying attention to. And there was this one, species of fish that the model could recognize, but the way that it recognized it wasn't actually recognizing the fish. That was like a very common fish for people to like take pictures with and pose with. So the vast majority of the pictures of this species of fish had like hands underneath it. So like when they did this, they saw that what the model cared about was just if there were like fingers underneath the fish holding it up and not actually looking at the characteristics of the fish, And so that's an example of a case where or a good example of why you need robust data, but also a good example of, we don't really know what the hell it's looking at. We just sort of know that it works.
I'll put it this way. It's like, if I asked you to explain how you come to a solution of a certain problem, you could give me a series of logical steps. So like, for example, like a physics problem, right? And you did it, you've done all these steps, you've shown your work. You can explain to me exactly how you got to the solution that you got to.
Maybe you can't, not me in physics.
That's a you problem. If I train a machine learning model to be really good at doing physics problems, and I ask it to explain itself, it either won't be able to, or it'll explain a completely different method to what is expected. So maybe it recognizes words in the problem and immediately just jumps to a conclusion, rather than taking the whole problem and doing all these logical steps. So kind of think of it that way.
Oh, I have a question. So
Yes.
I think GPT-4 does something where like it explains its like logical steps before like coming to a conclusion to an answer. Like how does that?
Great question. We're not open researchers. We don't know.
Transformers are very complicated and scary. I mean, I'm not entirely sure. Like, again, there's no way for us to really know that what it's saying is true. It could be that this is actually an accurate representation of what's going on inside of its head, or it could be it comes up with its answer. And then it's like, okay, if I know that I came up with this answer, what is a logical approach I could take to get there? It's sort of like if you ever did mental math really quickly, and then you have to show your work, you don't actually, if you're doing 8 times 8, you don't actually do whatever system your teacher wants you to. You probably just have memorized 8 times 8 is 64, But if your teacher's asking you to show your work, you're gonna be like, okay, well, what I did is, I don't know, I broke it apart and then I multiplied, whatever, I don't know, whatever it is to show your work. So just because it explains itself, because we have no idea what exactly is going on inside of its brain, we don't know that the explanation is right. It gives us, essentially all we know is that when we ask it to explain itself, it's giving us an explanation that seems like it can make sense. We don't know that's actually what's going on inside of its head, I mean, I guess that's also kind of the classic philosophical dilemma of how do you know anyone else is conscious? But that's I don't know. I don't like philosophizing like that.
So from my understanding of how they train ChatGPT and their generative models, they typically try and incorporate human feedback at some point. Recently, they've kind of created new models to model human feedback to the actual output. If I had to guess at how it's doing the explanations, it's basically just getting trained to match what humans expect. So yeah, that's why what Jackson said about it seeming to be correct is really important to recognize. And like, you know, it may be able to explain how to do like a basic calculus problem, but if you ask it to try and present a proof on some unsolved problem in mathematics and it explains logically, that will probably get picked apart by people who are qualified in mathematics. So
yeah, it's actually interesting. Benson just made a post on the Discord server about like explainable like proofs for anyway, sorry. You had a question?
And you're not
Well, that's a hard question. So, whoa.
like, I can tell you have this day, but I can't tell you why. But you know that you can trust me with this conclusion, something like that. I don't know if like something would help with the ethical concerns.
There may be something there, like maybe in a couple of years there'll be a research paper on like applying zero knowledge proofs to explainable AI. But I think one thing that we can consider is the idea with a zero knowledge proof is that you are showing them something without telling them everything that you know, right? So was it the Wired video with like Amit Sahai?
Oh yeah.
Yeah. So like, yeah. So the entire idea in his video is that he basically has like this large Arctic landscape, right?
Yeah.
And then he claims that there is a penguin on this like large picture. So imagine like this entire whiteboard is the Arctic landscape, and I say there's a penguin somewhere on it. But I just covered this and it's all black and you can't see anything. Now I'll poke a hole exactly where this penguin is. But I can move this sheet. So let's say I have a really small sheet, a much larger sheet covering it. I can shift this sheet and poke a hole anywhere and have the penguin appear there. So I've told you that I know where the penguin is. There exists a penguin, but I've not told you where on this landscape it exists. So the entire idea of zero knowledge proof is that you're hiding information. So you're not revealing information for security purposes. One thing that is being done currently, like medical fields in regards to explainable AI. So like with ChatGPT, for example, the data it trains on is very different compared to like if you want to create a machine learning model that will tell you whether a tumor is cancerous or not. They're not really words associated with that image because you won't have a doctor saying, okay, I zoomed in at this amount, then I saw these type of cells. It's very hard to do that. Our machine learning models will think about in terms of pixels and like the colors and shape and things like that. So instead, what a lot of machine learning models are now doing is they just highlight a certain area, and then they tell, oh, first look in this area. There's a high probability that there's something wrong here. So one thing that is happening is that we're offloading the explainable portion off of like machine learning to the actual human counterpart in a case like that. So what a lot of like software that does tumor detection or breast cancer detection and things like that, will just give you a highlighted area and then it's up to the doctor to actually then further make that diagnosis. So I think like the main bridge that would have to happen between like a zero knowledge proof and like the neural networks portion is like the difference between hiding that information. Maybe there's something there. It's a very hard question. It's very interesting though. Yeah.
So just like great questions, great discussion. We're nerds. We love talking about it. But just one last thing, just to touch base. We've covered a lot this quarter. Talked all about gradient descent, k-nearest neighbors, linear and logistic regression, all about using NumPy and pandas and implementing machine learning models from scratch. We hope you guys enjoyed it. This was all considered shallow learning, right? So as we say here, a good Python library for shallow learning is scikit-learn. But there's tons of other concepts in shallow learning, but if you want to really get into the juicy stuff, the deep learning, not the shallow learning, come check out advanced track and then eventually projects track. Also, one last plug for the AI reading group. Actually, when you were talking about like, you know, we're talking a little bit about cryptographically like secure AIs, and that was the topic of 2 weeks ago. I think we recently had one from Benson on that, which was a very interesting talk. This is going to be Jordan. It's a phenomenal presentation. Like, I cannot recommend it highly enough. You know, he brings his zeal, and he shows you all of this stuff. And man, I'm not gonna lie, I don't get most of it, but like the stuff I do get is pretty cool. So I'd highly recommend.
And one quick thing. If you are free this Wednesday, 6 8 p.m., you can come to Advanced Track, because Advanced Track, we're covering, the title of this week is just called Modern Deep Learning, which is, we're basically surveying every single like modern techniques with deep learning. It's gonna be a little confusing, maybe to see, basically assume that you've looked at everything before in Advanced Track, but it's a pretty good time where you like get on the comments, get a feel of like, here's where modern machine learning research is at, and here's all the topics that you will be looking at. Yeah. So yeah.
Yeah, but yeah, attendance code as always, and please, great questions. If you have more questions, please come down, you know, talk to us, ask away. We love talking about this stuff. We have a real passion. But yeah, thank you guys for a wonderful quarter. Hope to see you next quarter in Advanced Track. Woo! Great job.